everybody. Good morning. It's a place for me and for all the organizer committee to give you the welcome to our CaRT 2025. This occasion, we have 6 invited speakers, and moreover, we have a lot of participation of video talk and poster to some other colleagues and students. So let me to give the word to Hannah Formanki. Thank you, Hannah.
Thank you, Rita. It's my great pleasure to introduce our first invited speaker, Dr. Urszula Bednarz. She is assistant professor in the Division of Discrete Mathematics at the Rzeszów University of Technology. Her research focuses on discrete mathematics, but in particular graph theory and combinatorics. She contributes to several areas, including some structure graph theory, domination, distance domination problems, structural properties of graphs, colored graphs, and many, many others topics. Her activity field also includes some organizational activities at her faculty. She is a vice dean for education at the Faculty of Mathematics and Applied Physics. So it is really a great pleasure for us that all of you accepted our invitation. So now the floor is yours. Please give us a first talk on our conference.
Okay, thank you very much, Hania. Now I choose my presentation. Okay, it's everything is okay?
Yes.
You can see it?
Yes, we can see.
Okay.
Yes.
Okay, thank you. Once again, I would like to start with thanking Rita for the invitation to speak here today. It is a great honor and a great pleasure to be here and be part of this conference. In my talk, I would like to present a special type of dominating sets, namely one-to dominating. And also I will talk about one-to dominating sets with additional restrictions. I start with a classical definition. A dominating set of a graph G is a subset D such that every vertex outside D has at least one vertex in D. And as on this graph, as you can see, the dominating set consisting of green vertices, because every black vertex is adjacent to at least one green vertex. Over the decades, many generalizations and modifications of dominating sets have been proposed. And in 1985, Fink and Jacobson introduced a multiple domination, called also as K-domination. And here is a definition. A subset D is a K-dominating set of a graph G if each vertex outside D has at least K neighbors in D. If K is equal to 1, then we obtain one dominating set. It is a classical dominating set. And if K is equal to 2, then we obtain a two dominating sets. Among K dominating sets, two dominating sets are most often considered. It follows from the fact that the existence of K-dominating sets in graphs requires large degrees of vertices in graph, significantly reducing the classes of graphs which have such a set. And in this picture, it is an example of a two-dominating set consisting of red vertices. Every black vertex has at least two neighbors. Here, every black vertex has exactly two neighbors. some properties of two dominating sets and independent two dominating sets are given in these papers. And in 2008, Hedetniemi and others introduced a weaker version of multiple domination, which admits a distance domination. And here is a definition. A subset D is a 1K dominating set of a graph G if every vertex outside D has a neighbor in this set D, and another vertex is at distance of at most K from this vertex. And if K is equal to 1, then we obtain a 1-1 dominating set, which is a 2 dominating set mentioned earlier. And if K is equal to 2, then we obtain a 1-2 dominating set, which is also called as a secondary dominating set. Of course, the set of all vertices in a graph is also a 1K dominating set. It was proved that the study of 1K dominating sets makes sense only if K is equal to 1 or 2 or 3. And here is an example of a 1-2 dominating set in such a path. Green vertices form 1-2 dominating set, and every black vertex has one green neighbor, and another one is at distance of at most 2. Here exactly this distance is equal to 2. And here is an example of 1-1 dominating set. Every black vertex has 2 green neighbors, and of course every 1-1 dominating set is also 1-2 dominating set. That is, any 1-1 dominating set is a subset of a 1-2 dominating set. And in these papers, many applications of 1-2 dominating sets, also complexity issues, interpretation, independent domination sets in graphs and their products are studied. If we consider the family of 1-2 dominating sets of a graph G, then a family of 1-1 to dominating set is a subset of this family, and it is presented in this picture like as a red set. Next, if we consider a subset by excluding the cases that are 1-1 dominating, then we obtain class of proper 1-2 dominating sets. And this class was introduced by Adrian Michalski. Formally, a definition of this set is given here. A subset D is a proper 1-2 dominating set of a graph G if it is 1-2 dominating and not 1-1 dominating. And example of a proper 1-2 dominating set is given in this path consisting of green vertices, and as you can see, there exist vertices, these 2 black vertices, which are not 1-1 dominated. And here is black vertex, which is 1-1 dominated. And because the set of all vertices in a graph is 1-1 dominating, that then it is not, of course, a proper 1-2 dominating. And this raises the question about the existence of such sets, and it was proved that a connected graph has a proper 1-2 dominating set if and only if this graph is not a complete graph. The problem becomes more complicated if we require that the distance 2 must be achieved for all vertices outside the set D. And that's why we introduced the concept of perfect one-to dominating sets, a special case of proper one-to dominating sets. And we will consider such green subclass of proper one-to dominating sets in which the condition is satisfied that every not like it was in the class of proper that there exists. Here, every vertex outside D is perfect one-to dominated. And this is a definition. A subset D of a graph G is a perfect one-to dominating set if it is one-to dominating, not one-one dominating, and every vertex outside D has exactly one neighbor in D. And to illustrate this definition, let us consider a path of order 6, and these 3 types of domination mentioned earlier are shown with a dominating set consisting of green vertices. This is a one-to dominating set. This is a proper one-to dominating set. And the last one is a perfect one-to dominating set. A proper one-to dominating set, as I said earlier, this is an example of this set, requires the existence only at least one vertex, which is not one-one dominated, but is one-to dominated, and this is these vertices. In perfect one-to dominating set, this condition imposes on all vertices outside D. So here every black vertex is one-to dominated, but is not one-one dominated. We can also say something about applications of perfect one-to dominating sets. For example, one of them is related to wars and natural disasters. Towns, if we towns located in vertices on this path and edges connects these towns. In such situation, a perfect one-to dominating sets can ensure that each point, town, or a strategic location has access to a primary shelter or a resource hub with additional backup shelter located at a greater distance. This ensures that in case of emergency, all points have a safe and reliable refuge, even if one shelter becomes inaccessible due to unforeseen circumstances, some circumstances. And it is one of the examples. We can also find another. It is obvious that the set of all vertices is not a perfect one-to dominating set, and because it is one-one dominating set. And while the problem of the existence of proper one-to dominating set has already been resolved, the existence problem of perfect one-to dominating sets remains more difficult to solve. Of course, not every graph admits a perfect one-to dominating set. For example, triangles and complete graphs do not have a perfect one-to dominating sets. We have studied the existence problem of perfect one-to dominating sets in graphs and obtained a complete characterization of graphs which have such sets. And to show this, we use the following symbols which denote the minimum and the maximum degree of a graph G, and by S we denote the set of all vertices of maximum degree. And it was proved that if graph has leaves, then it has a perfect one-to-dominating sets. And the problem of the existence of such sets becomes more challenging, more interesting if we consider graphs without leaves. And that's why we assume that the minimum degree of a graph G is greater than or equal to 2. I will present selected cases in each of them. A full characterization of graphs with perfect one-to-dominating set is given. And if maximum degree is equal to n-1, the problem of existence is the simplest. And if maximum degree of a graph is equal n-2, then the situation depends on the cardinality of the set S. Because the larger the size of S, the more possible cases that must be considered. And if we increasing the number of vertices of maximum degree, increases the number of neighborhoods that must be analyzed. And in the following theorem, we give the necessary condition of the existence of a perfect one-to-dominating set in case when graph has one vertex of maximum degree equals n-1. If graph has a perfect one-to-dominating set, then this graph has the unique vertex of maximum degree. And the following theorem, in the following theorem, we proved the necessary and sufficient condition of the existence of perfect one-to-dominating sets. And a graph has such a set even only if the vertex of maximum degree is a CaRT vertex. And as an example of graph which satisfy this theorem, we consider such a graph, and this is a vertex of maximum degree, and it is also a CaRT vertex, because if we remove it, then we obtain disconnected subgraph with 3 components. And a perfect one-to-dominating set is a set consisting of these green vertices, and every black vertex is perfect one-to-dominated by green vertices, because all vertices, black vertices outside this set are adjacent to a CaRT vertex, and another green vertex at distance 2. And even if the case when we have only one vertex of maximum degree equals n-2, we have to analyze relations between neighborhoods in these graphs and neighborhoods of vertices in these graphs, not only neighborhood of a vertex of maximum degree, but also we have to study relations between neighborhoods of others vertex in graphs. And here we give, in this case, complete characterizations of graphs which have a perfect one-to-dominating sets. We have to consider if open neighborhood of the vertex of maximum degree induces a connected subgraph, and it is presented in this theorem, or disconnected subgraph, and it is presented in this theorem. And the graph has a perfect one-to-dominating set even only if are satisfied the following conditions. When considering 2 vertices of maximum degree in a graph, we must examine whether their neighborhoods are the same or distinct, and also we have to consider if these vertices of maximum degree are adjacent or not adjacent. And in this case, we also find fully solutions for the existence of perfect one-to dominating sets. And here is case presented in this theorem case when two vertices of maximum degree are not adjacent and graph has a perfect one-to dominating set, even only if there exists a vertex of degree 2 in this graph. And in next theorems, we proved the existence of perfect one-to dominating sets if these two vertices are adjacent and their closed neighborhoods are the same, or like in this theorem, are different. And the next case under consideration involves three vertices of maximum degree. And even adding just one more vertex of maximum degree significantly increases the number of possible configurations that must be analyzed. In particular, we need to consider whether the selected vertices are adjacent or not adjacent, and also we have to study relations between their neighborhoods. In this case, also we obtain the complete characterizations of graphs that have a perfect one-to dominating sets. And in this theorem, under such assumption, we consider case when three vertices of maximum degree are x, y, z, and x and y are not adjacent, and z is adjacent to x and y. And the neighborhoods satisfy the following condition here and here. And a graph has a perfect one-to dominating set if and only if there exists a unique vertex in a graph G of degree 2 adjacent to x and y. And here is an example of such graph which satisfy assumption of this theorem. X, y, and z are vertices of maximum degree. Here is the unique vertex of degree 2. And of course, the relations between neighborhoods are satisfied on this graph. And here, these two green vertices form a perfect one-to dominating set, or these two red are also a perfect one-to dominating set, form a perfect one-to dominating set. Every black vertex is in this graph is perfect one-to dominated by these red vertices or by these green vertices. And in the next theorem, we study next possible cases which may in graphs B. For example, here in this theorem, all vertices of maximum degree are adjacent and their closed neighborhoods are the same. And here we also find a necessary and sufficient condition for the existence of a perfect one-to dominating set in this situation. And here is a graph which satisfies this theorem. X, Y, Z, three vertices of maximum degree equals n minus 2, and they are adjacent. Here is the unique vertex U, which is not adjacent to these three vertices of maximum degree. And if U is adjacent to V, then they form a perfect one-to dominating set. And it is an example of here, it is this situation from the theorem. And of course, we also study next possibilities. Still, vertices of maximum degree are adjacent, but their closed neighborhoods satisfy the following condition. And the last possibility in this case, when vertices are adjacent of maximum degree and all neighborhoods, the closed neighborhoods of these vertices are distinct, then there is no perfect one-to dominating set. And as you can see, we study vertices with large maximum degrees, but we also study the existence problem of perfect one-to dominating sets of small degree, namely subcubic graphs and 4 regular graphs. And now I recall definitions. An regular graph, it is a graph in which all vertices have the same degree equal to R, and a cubic graph is a 3 regular graph. A subcubic graph is a graph if the maximum degree of a graph does not exceed 3. And in this theorem, it was proved that every connected subcubic graph with at least 5 vertices contains a perfect one-to dominating set. Moreover, a perfect one-to dominating set can be constructed in polynomial time, if it exists. This situation changes when the maximum degree of the input graph increases by just 1, and we proved the following theorem, that the existence of perfect one-to dominating set in a 4 regular graph is NP complete. And at the end of my talk, I would like also mention about adding the restriction of independence to dominating set. And for special types of domination, we can also add the restriction about the independence. And then we obtain independent dominating sets, which also are called kernels. And of course, if we can also add the restriction to one-to dominating set, restriction of independence, and then we obtain a one-to independent dominating set. And even this simple path of order 4 has one-to independent dominating set consisting on these 2 red vertices, because every black vertex outside this set is one-to dominated by 4 red vertices, and also these 2 vertices are independent. And it was proved that the problem of the existence of one-to independent dominating set in an arbitrary graph is NP complete. And motivated by the concept of a one-to independent dominating set, and also by independent 2 dominating sets, we introduced and studied just like we introduced the definition of one-to independent dominating set, which is just like a mix of these 2 definitions. And a subset J is a 1-1-2 independent dominating set of a graph G if J is independent, and for each vertex outside J there are 3 distinct vertices such that 2 of them are adjacent to X and the third one is at distance of at most 2 from this vertex. And of course, every 1-1-2 independent dominating set is also a 1-2 independent dominating. To distinguish this new type of independent dominating set, we consider the case when the parameter is 2 is attained. And it turns out that in this type, 2-palm plays a special role. And this is a 2-palm. In this graph, of course, it has a 1-1-2 independent dominating set because every black vertex has 2 red neighbors and the third one is at distance 2. And we also proved that the existence of a 1-1-2 independent dominating set in an arbitrary graph is NP complete. We also introduce a stronger notion of 1-1-2 independent dominating set as we introduce a strong 1-1-2 independent dominating set. And this is a definition. Subset J is a 1-1-2 independent dominating, and if for every vertex outside this set there exists a vertex in this set that the distance between these 2 vertices is equal to, then J is a strong 1-1-2 independent dominating set. Why we introduce such sets? Because we can construct graphs in which the number of strong 1-1-2 independent dominating set is the fixed number often given by the recurrence relation. In particular, we proved that we can construct a graph in which the total number of strong 1-1-2 independent dominating set is equal to the well-known Fibonacci or Lucas number. And now I recall well-known numbers. Fibonacci and Lucas numbers are given by the following recurrence relations with such distinct initial condition. And as you know, they have many interesting applications. There are a lot of generalization of these numbers and also interpretation in graphs. And graph interpretation was of Fibonacci and Lucas numbers was initiated by Prodinger and Tichy. They proved connection between Fibonacci and Lucas numbers and the number of all independent sets in a path and in a cycle. And their results gave an impetus for studying these graph parameters in other classes of graphs and their products. And many graphs parameters can be expressed using numbers of the Fibonacci type, and it is also presented in this paper. And now I present what I told earlier, I present now a construction and an interpretation of Fibonacci numbers due to the number of all strong 1, 1, 2 independent dominating sets in a graph. And by this symbol, we denote the number of all strong 1, 1, 2 independent dominating sets in a graph. And we proved that we can construct a graph such that this number is equal to nth Fibonacci number. And here is a construction of this graph. As you can see, this is a join of n-1 for cycles and 2 palm, which I mentioned earlier. And here is an example of strong 1, 1, 2 independent dominating set, which is formed by green vertices. As you can see, every black vertex has 2 green neighbors, and another one is at distance 2 green vertex. And all green vertices form independent sets. Similarly, we can construct a graph that satisfies the number of all strong 1, 1, 2 independent dominating set is equals to nth Lucas number, and it is presented in this theorem, and we can construct such a graph which is similar to mentioned earlier, but we add this edge. And here is an example of a strong 1, 1, 2 independent dominating set in this graph. And these green vertices form this set. And it's all what I want to present today. And thank you very much for your attention.
Thank you very much, Ula. Yes, bravo. Do we have any questions, remarks? Maybe somebody on YouTube. Julian, do we have any questions? Yes, Rita.
Okay, so thank you very much, Urszula. Very, very nice talk. I enjoy a lot. Thank you. It's very nice when we see this connection between graph theory and number theory with this Frobenius and Lucas number. So this is very, very nice. And I have 2 questions. I don't know if my first question is if you have a characterization of trees for one of this type of AB dominating set, or and the second is if you play with some operation, for example, subdivision or some product of graph or something like this.
But it is connected with the first time, the first of my talk,
Yes.
1, 2 domination.
Yes. Or of the second 2. It doesn't mean.
So yes, independent domination, 1, 1, 2 independent domination graphs were studying in products or and in other graphs. We also find graphs which have the same cardinality. Not only we count the number of all these sets, but also we try to find graphs where the cardinality of these sets are the same, and we have different results connected with this. And the first question, can you repeat it?
The first question is about characterization, I don't know, for example, of trees or... I don't know if it has sense the question, but because I remember now that are you talking, I remember that for the case of independent dominating set, there is a characterization for trees. Yes, this is.
Yes, yes.
So I don't know
Yes.
if in your case.
Yes, we about independent 2 independent dominating sets. We also say as kernels 2 kernels. We study in trees, and also we consider different graphs. But in a tree, it is 2 independent dominating set.
Okay, thank you. It was my question.
Thank you.
Okay, thank you, Rita. Do we have any other questions?
I have one question.
Yeah.
As you can define the 1-2 dominating set, maybe you can extend that definition to an HK dominating set. Like you have one vertex at distance at most h, and the other at distance at most k. Do you know if that problem has been studied, or if it is equivalent to the 1-2 or 1K dominating set or something like that?
1K dominating set are studied in the literature, and as I said, it makes sense if K is equal 1 or 2 or 3, but we also try to solve problems of the existence a perfect 1-2 dominating set if K regular graphs. I know that it isn't the same what you are asking, but it is very difficult to solve this problem. But 1K dominating sets mostly Nagy studied, and more interesting are when distance it isn't very big between one neighbor and another one, and not in the long distance, because the graphs must have a lot of vertices with large degrees, and it significantly reducing such classes of graphs.
Yeah, you can add like whatever vertex and it works.
Yeah, it's easy. It's easier than it is distance 2, for example.
Okay, thank you very much.
Thank you, Julian. Any other questions, remarks? Actually, I have one. Thank you, Ula, for applications of this model. You mentioned shelters, post-disaster
Yeah.
management, yes? Could you tell once again how it can be applied? What is the particular... what is important in this problem 1-2 domination, that it can be solved, find solutions find applications in such a problem?
I told about it. I try to find because there are some applications similar to this, what I told, connected with 1-2 dominating sets. But I told that it could be important when we have such natural disaster or wars, because we always have backup shelter, or in backup hospital, for example.
Okay.
So if we
Facilities.
have a distance nearby, and it is, but we can also find if something happened, then we have also backup in the second shelter or a hub. I told about war because we are nearby war with Ukraine, so maybe, but we can also say the same about pandemic and hospitals.
Yes.
So maybe
Fire stations.
we shouldn't say about wars,
Yeah.
but it's for us.
Okay, thank you very much. Any other questions? No, Julian on YouTube?
No questions on YouTube.
No questions on YouTube. So thank you once again, Ula, for very nice, interesting talk.
Thank you.
And now, yes, we thank you a lot, you. Now we have 13 minutes break, yes, Rita?
How long?
Yes, we will continue at 11.
At 11. Okay.
In,
6 p.m. in Poland.
I don't know,
Okay,
12
we'll make
minutes,
another-
something like this.
We'll make
Okay.
another cup of coffee then.
Yes.
Okay. So see you in
13 minutes.
10, 12 minutes, more or less. Thank you very much to everybody.